the three most common questions I basically get as part of any of my presentations is how do I reach you? How do I contact you? How do I ask you questions? Where can I connect with you? And where do I get this presentation? These are the three most common questions I get when I do any session. So all of these are answered in this slide. And basically this slide is the only slide you really need to take a picture of. All the other slides, you can just download the presentation later and you'll get everything. So if you really want to take pictures or make notes, this is the slide you need to take a picture of, and you get the deck at this location, as well as once the APAC tour concludes, this will also be uploaded onto their site along with the recording. So we started off a bit late, so I may have to speed up a bit to cover some more material. But here's kind of the thing. So there's about 6 presentations in this conference on machine learning, and many of them kind of center around ADW. So what I thought is I'll kind of do something slightly different. I'll focus more on algorithms and basics, where it will give you a good building block when you go to the other machine learning sessions that are there through the course of this tour. So the first thing that's always the question that I get from DBA is always is, hey, what am I going to do? My job role is changing and evolving. And usually what DBAs are doing are architecture planning, data security, working on performance tuning, configuration patching, provisioning, backups and disaster recovery, as well as database performance tuning and SQL optimization. These are the most common things they do. When you move towards autonomous, as well as more newer versions of databases come out, more and more the things at the bottom and the maintenance tasks kind of start getting scratched out. Provisioning has FVP for faster provisioning and patching. There's autonomous, doesn't require you to do backups or provisioning or tuning or any of that stuff. You just click and you create a database and you've got most of that stuff. That doesn't mean that you don't have stuff to do. You just have more stuff on the value scale where you actually have to focus on data security, cybersecurity, service level management, application related tuning, and some of these other things. So one thing that's actually kind of shown up over the last couple of years is the whole machine learning area, right? So machine learning is kind of like, it's painted as this wildly complex thing that people have to kind of learn. And then once you know the algorithms, then you can do a whole bunch of interesting stuff, but that's not actually true. So all this began with, most of us are, as DBAs, are familiar with this space, right? So we know what dashboards are, we know reports. We've been working on Apex for quite some time. And then we go into more diagnostic analysis where you're trying to predict like root cause and stuff like that. And then you go into predictive machine learning. It's like, what will happen? Like, so for example, if it's summer, is there going to be more beer needed in California or not? You're trying to predict when things will happen and what will happen and how those events are correlated. And then you go to machine learning apps. You upload your photographs. It tells you there are dogs and beach, and there's a whole bunch of beach pictures in your collection. Or you want to say, I want to search for dogs that are playing on a beach and with me in the picture. So these are ML-enabled applications, right? So this is kind of the direction with which analytics has actually been moving. And most of this stuff is something as DBAs we're familiar with. But there are 2 roles that are significantly evolving. One of them is the data engineer role, which is basically like you take the data, you organize it, and you architect the entire data mart, right? So that the person who wants to analyze this data can basically take it to the next level. So this is kind of like ETL evolved. And then you're the machine learning or the citizen data scientist who basically takes this architecture that's being built and tries to solve real world problems and trying to make predictions and insights and stuff like that. The 2 most important aspects of this entire job role is, first of all, everyone knows what data warehousing ETL is. Data cleansing, data validation, normalization. Remember, normalization is the process of taking data from multiple tables and trying to combine them in such a way so that you require fewer number of accesses to basically pull the same amount of data. So first normal form, second normal form, third normal form, boy squad normal form. That's the different kinds of normalizations. And then you want aggregations, which are basically materialized views. And then you want data deduplication, where you have clusters, which I'm not talking about like database clusters. I'm talking about clusters where you have index clustering, where you kind of try to store data together, or index organized tables. These are examples of data deduplication or storing data closer to the proximity of the index so that your access can be as quick as possible. We know all this stuff. As a DBA, we've kind of done this. So where does ML come in? First thing, it's a toolbox and it's not hard. It's just a new feature. It's no different than normalization, materialized views, push down union view predicates, or any of the stuff that you already have learned before. It involves data wrangling. It involves new attributes or a process called feature engineering, and we'll discuss this a little bit going forward. You can improve and import these predictions and insights, and then you translate this and build machine learning models, and then you automate the entire thing using something called a CI/CD process using ML ops. So these are the different kinds or forms of things that you have to do as you evolve more into a database developer role as part of your current job. One thing is, if you had basically more time, you'd spend more time trying to think about the problem and how to basically tackle this problem, what kind of model will you need, versus you spend a very small amount of time trying to actually build the models, trying to lay the algorithms and do AutoML and all that. That's actually a very, very tiny portion of a machine learning project. And majority of the time, you're basically doing ETL, feature engineering, trying to figure out what's the right model and algorithm combination to choose. And then all the AutoML does is basically building the model. And all that takes the least amount of space. So spend more time thinking of your use case, thinking of what inputs that are basically going to go into your features and stuff like that, rather than trying to say, oh, I'm going to try this model, I'm going to try that model. And then you don't really know what you were trying to address in the first place. There are different categories. So first of all, machine learning is kind of targeted at three main categories of people. So first is academia, right? So this is people on the cutting edge. They're basically trying to find statistical relevance to these algorithms. They're trying to explore new developments. Things change every 3 months in the space, and you really need to be in depth in terms of these mathematical algorithms and how they work and how they're correlated. You have to be very familiar with this field. And there are conferences like NIST and ICML that you can attend where you want to be cutting edge on this stuff. So this is first category in academia. The second category of people is people like model builders. So basically, you're not a guy who, you don't want to be on the cutting bleeding edge, but you build models. You take use cases, you match the algorithms, you perform your A/B tests, and you deploy these, you perform hyperparameter tuning, and you say, yep, that model is good, and you deploy the use case. So you're a model builder. The third category of people are model consumers. You don't know anything about the algorithms. You're not that great at maths. You know what somebody has already built. You just know that this algorithm or this model matches this use case. So for example, I'm uploading my pictures to Google, and Google's automatically figuring out how many dogs are there, how many, which dog is playing on a beach, how many of them contain pictures of my kids. I'm a consumer of this. So I'm using applied machine learning. I don't know the algorithms. I don't know whether they're using CNNs or RCNNs or 3D RNNs or what kind of algorithms they're using to do image analysis, but I just consume them. So the models are basically an inference engine. So anytime I want to consume something, I have to apply patches, or basically I just upgrade the version of the software I'm running, and then I'm consuming this model. So these are three basic categories, and most of us as DBAs or developers will basically fall into either the model builder category or the model consumer category. But it's okay to be in either one of these categories, because the goal is to basically find which of these machine learning use cases match my particular problem, right? There are four basic categories of machine learning. The first one is supervised learning. Supervised learning is nothing but an expert system. So you define something, there's a bunch of rules, it follows the rules. It's great, it doesn't deviate from it. Semi-supervised machine learning is where there are certain patterns within the data, and then you basically define certain basic ground rules for what the system is supposed to do. And then the system uses that feedback to improve its own accuracy. In other words, after some time, the system could possibly be doing 85% of the predictions with 15% human input in terms of self-correcting. So the human will come and say, hey, this decision you made is not exactly right, and you need to kind of change that. And it goes ahead and makes a change to that particular thing. The third category is reinforcement learning, which is basically a reward-based system based on a certain kind of an action. It is also very used, it's very commonly used in gaming environments. So you remember when we were younger, like we used to kind of like play chess, right? So I remember as a kid, I used to play chess, and I used to go to this, I had this Intel, 80386 computer, and I used to play chess, and it's like, I picked the easy level, and I used to defeat the computer every time. And I'm like, yay, this is great. Now, if you play this, the computer, even on the easy level, starts kind of getting better because it knows your moves and it uses your own moves against you. So as the computer gets smarter and smarter, it has the capability of making better decisions. And eventually it's like, it's like the computer that basically defeated everybody in chess or Go, right? Which is the AlphaGo thing for the Google DeepMind stuff. where you use reinforcement learning and the computer basically learns all your moves and uses your moves as a collective hive mind against you and eventually defeats you and then goes on to the next player and the next player and the next player. That field is called reinforcement learning. But reinforcement learning is also a category that's very popular for predicting different kinds of problems. When is the CPU utilization of this machine exceeding 75% and it's going to cause a system crash? These are examples of reinforcement learning. And the last, but the most popular category of lately, so semi-supervised machine learning, by the way, is used for AI or AI ops related categories, where you're looking at CPU memory utilization and you're troubleshooting an IT environment. Unsupervised learning is used for all sorts of other kinds of use cases where you feed it a whole bunch of data and it's going to try to predict insights out of it. Like if I give it transaction data, it may say, by the way, seems like in this part of California, most amount of fraud happens, and it happens with people which are in the age groups of 18 to 24. So it is smart enough to pull out these patterns, which you would not think of. So it's like you give it data, you don't know what questions to ask, but the system is smart enough to say, this is what you can ask. And these are exploratory algorithms, and they're called unsupervised learning algorithms. So you basically, without any external input, it's going to tell you what can be extracted from this data. So these are 4 broad categories, right? So within these categories, there's different subcategories. So the first subcategory is regression. So regression is a nature of a machine learning algorithm, which can be used to predict numbers. So regression, as you can see the term, it applies to numbers, right? When is this stock going to go higher? When is this customer going to leave me? When is the best time to buy a house? When is the best time to buy beer? Or which item should I buy now? So, hey, I have a birthday party, like for the next 5 months. I have these kids and these are the kids' ages. When's the best time to buy the gifts? So I can buy them cheap and I can buy expensive gifts for cheap and I can go give it to the kids when their birthdays arrive. These are examples of regression algorithms where you do number predictions and you try to find which is the optimal time or in the scale of the number to basically perform this transaction. So this is the first category, subcategory rather, regression. The second one is classification. I'm trying to classify a bunch of flowers based on their characteristics, like their smell, the insects they attract, the petals, number of petals they have, the colors, when do they bloom. These are the examples of classification. Or I want to find out which customers shop the most when I give them deals, or which customers shop the most, even though I don't give them any deals. Which customers are most likely going to leave if I don't give them any deals? Or I'm seeing fraud in a certain area. What kind of transactions do I need to monitor to ensure that people that are actually conducting legitimate transactions are not blamed for conducting fraud? Classification algorithms. So this is the second subcategory of algorithms. The third is clustering. Clustering basically takes things and puts them in a segmentation kind of a way. I want to know where can I open an ice cream store and which are the most common categories of ice cream that people eat in this area. I'm trying to do credit risk evaluation. So I'm trying to find out which area can I target where I can sell credit reports to people who I know will actually go for it. Document similarity. So I'm trying to look for summaries of a particular book, and I'm trying to figure out who are the other people that read this kind of book. So it's a mix of not just the book, but the kind of influence around you in terms of people who read that kind of book. So that's document similarity combined with graphs as another example, right? So clustering is an extremely powerful example to find membership of an inferred class, and is the third subcategory of this. Fourth one, anomaly detection. Now remember, these are just terms to give you a broad idea, right? Machine learning is a huge topic. I mean, I can go talking on this topic for the entire day, but I'm trying to give you something in 45 minutes that you can take to the other sessions that will kind of take it to the next level, all right? So anomaly detection is basically like you're trying to figure out when something is out of sync. A CPU utilization of 85% for this machine at 9 a.m. in the morning, is that normal or not? This person normally walks 10,000 steps a day. Today they walked 8,000. Is that normal? Or maybe there was there were guests at home, or maybe they had a call, or maybe they're having a heart attack. So how do you find that, right? So these are the kind of things that anomaly detection. And this is one area that I work a lot in, because if you're working in AI ops and IT related systems, right? anomaly detection is actually one of the most powerful areas to work in. Associated rules. This is very good in shopping carts applications. These guys bought this, so you might actually have to buy this. Most failures when customers have installed, say, Oracle 19c, are when they created an SGA of greater than 2 terabytes. So this is kind of association rules to trying to find either like-minded people or harbingers of failure, where you know that if enough people do something like this, things will start failing, all right? So that's association rules. Time series is not an algorithm per se, but it's kind of a data and the algorithms that operate on top of this data. So here's a couple of things you need to know about time series. So time series is where, first of all, everything has a temporal aspect. So it's value over time. That's kind of the way this works. You find things when they're hitting a threshold and you can forecast anything. When is the CPU utilization of this box going to hit 90% and the box is going to crash? When is the capacity of this machine going to exceed? When is this disk group going to fill up? When is the best time to go to this movie theater when it's not going to be as crowded? All this can be predicted using time series. The seasonality of data means a repetitive pattern of occurrence. I drink coffee once an hour for the first 6 hours. That means my seasonality is 6 hours, and then it repeats after another 12 hours. I again go for another 6 hours. So that's my seasonality. The AWR takes a snapshot every 1 hour. So the seasonality of the AWR is 24 hours, because after 24 hours, you kind of complete a complete day. And that is a unit of analysis. So that's called seasonality of data. And this is time series. So everything that you're analyzing in a machine learning space that basically has time against value is basically a time series analysis. And there are many algorithms that operate directly on time series type data. Graph analytics. Graph analytics kind of combine with all the previous ones, but they basically have relationships. So when you're looking at fraud, you can say, hey, by the way, your friend was in the same area as you and he had a fraud. So there's a good chance that because you guys went to the same restaurant, that you might also have a fraud. Or there's a network outage in your city and there's your neighbor that the neighbor has no ideas that you are even that person's neighbor. But that person gets a message saying your neighbor had an outage. There's a possibility you may have an outage too. So you use graph analytics to basically combine the previous algorithms and kind of take it to the next level and find out how these relationships can be established. Neural networks is something that is extremely popular. We won't cover neural networks much in this conversation because we're going to go into more of the machine learning aspects of it. But typically, neural networks can also be used for classification, regression, as well as something called deep learning. Typical examples of neural networks are photo or image analysis, translation related activities, translate from language A to language B, facial recognition analysis, image recognition, fingerprint recognition, any kind of biorecognition analysis, right? And also you can use it for translation, any of the smart assistant-based systems. These are examples of how computers with different neural networks that has stacked onto each other. That's why you notice the neural networks have an input set of neurons. They have something called a hidden layer where a certain amount of processing happens. And then there's an output layer. So the hidden layer could be configured to send its output to the next layer or to suppress its output and not send it back to the next layer. And that concept is called forward or back propagation, all right? So basically think of neural networks as units of thinking that take certain input and then pass certain output to the next level. And then, you can have many of these stacked together. And these are used to recognize numbers, recognize faces, recognize photographs, dogs, cats, all of that stuff comes out of neural networks and basically deep learning algorithms. So in short, just to give you a summary of the whole thing, most of the top ones fall into the supervised learning, which is attribute importance, classification, regression. And the ones lower, which are clustering, anomaly detection, and associations, basically falls into unsupervised learning. So this is kind of a summary of all the previous slides I went through. It's important to understand these concepts. When you go into machine learning algorithms, now I'm only going to concentrate on clustering, regression, classification, and do a little bit of something called feature extraction or attribute importance, because these are the most common areas that you're going to play in, okay? And These algorithms, hierarchical k-means, orthogonal partition clustering, lasso model, ridge regression, these are names of different kinds of algorithms. Some of these are as old as the 70s. Some of these are brand new, which are probably as old as the 90s or the early 2000s. Many of these have been invented between like the 80s to now, and they've been optimized and there are multiple versions against it. There is no benefit in learning these algorithms as to what these algorithms are and how they work, because all you care about is running your model through it and finding out which ones are good. And we'll go into a little bit more details of how this actually works. Okay, so I just put this here just to know that if someone tells you, hey, how are we doing this using ridge regression? Immediately you need to know that this is a regression algorithm and these are the inputs, hyperparameters to a regression algorithm. You should know that. You don't care about how ridge regression actually works, but you should know how a regression model works and in which cases would you use a ridge regression model versus a lasso model. So that's something that's worth learning. How these algorithms work is not worth learning. There's an aspect that is very important that constantly pops up. It's called feature engineering. Feature engineering is basically taking a certain amount of inputs and changing them to new attributes. So think of them as, in the database, you can basically create these virtual attributes, right? Where you can say, hey, select this thing as age, because from current date to minus date of birth, you select it as age. It's the same thing as creating these virtual columns. You're trying to take a source attribute and trying to convert that into a new attribute, which makes more sense to the machine learning algorithms. For example, age makes more sense than date of birth. The distance I commute makes more sense than where I stay. The percentage of calls I make are a number of dropped calls, international calls I make are more important than my actual calls themselves. How much money do I make versus my peers is more important than my salary in itself. And based on my purchases, I can classify those categories into whether I buy more food or clothing makes more sense versus just the individual purchase records. So it's very important to tune the inputs or the features that go into a machine learning model. And this process is called feature engineering. The more you reduce the number of inputs or attributes that are actually going into your machine learning model, the faster the model converges and you can train it a lot more faster as compared to what it was before. We spoke about neural networks. Just a quick introduction. There are neurons, there's inputs, there's outputs, and there's something called weights and biases. So weights and biases are basically like if I'm taking a cup of coffee and say, for example, once I burnt my hand when I was holding a hot cup of coffee, right? So that memory kind of stays in my mind and it's called a recurring function. And when the moment I even see this cup of coffee, my hand's going to think twice, should I even bother holding it because I don't want to burn my hand. So you have that thought process that goes in. So that's the input. And then there's a bias. The input is grab the cup of coffee. Neuron is one activation function in my brain. The bias is I've been burnt before. The weights are every time I try to hold a cup that's basically made out of porcelain, I'll end up burning myself. But if I hold a paper cup with a sleeve on it, I don't burn myself as much. So that influences my weight. So if I see a Starbucks cup, I'll probably grab it without thinking twice. If I see a porcelain cup, I'll think twice before I hold it. Excuse me. These are called weights and bias functions in the context of a neural network. So this is introduction for you to understand these terms and how they work and how you can apply them going forward, right? So now, if I take everything we have done so far and I combine them all together, how do I build a machine learning project, right? So first of all, I can set the business objectives. So my objective, because I'm a payment provider, is to find fraud in my transactions as quickly as possible and identify and reverse those transactions before people have lost their money. First of all, I have to take all the payment records from all the systems and then clean them up and organize them in a single central location. So that's number two. The third one is I have to pick the most important columns from this, which is where did the transaction happen, who the transaction was with, who's the originator and who's the buyer, right? Sorry, who's the originator and who's the seller. The next third one is the location where this transaction actually happened. And the fourth one is the relative location where I normally perform these transactions. The fifth can be the number of transactions I have done and what percentage of those transactions have I reported fraud before. So these are inputs that I can say will determine most effectively if these transactions are fraudulent transactions or not. And they will determine the efficiency of the algorithm. Then I take input training data of past fraudulent transactions and I apply the algorithm to see, hey, this is a fraud, this is not a fraud, and train the algorithm. And then I take the live feed of transactions that are coming in and I try to see if it can find the transactions. Remember this, it has to find transactions that are fraudulent. In some cases, it may mark more than just the transactions that are fraudulent and mark the ones that are not fraudulent as fraudulent. That means the model is overfitting. And it's not great because I can't call a customer a cheat if they have not done a fraud. Now, the other side is I lose a couple of fraudulent transactions, but the ones I mark for sure, they are fraudulent transactions. So the goal is to get to 100%, but usually I'll end up coming up to like 95 to 96%. That process of tuning this is called either underfitting or overfitting the algorithm. The algorithm should neither underfit nor overfit. And you can tune this by changing the hyperparameters. Hyperparameters are input like init.ora for an algorithm, what an init.ora is for a database. That's what hyperparameters are to the algorithms. Each algorithm has got its own examples of hyperparameters. Like if you have random forests, you have to configure the number of trees. If you have decision trees, you can configure the n random values. If you have SVM, you have to configure something else. So each algorithm has a separate set of hyperparameters that you have to get yourself familiarized with. Once your training data and algorithm are good and you've identified most of the fraudulent transactions, you have a model. Then what you do is, there's this thing called autoML. AutoML basically takes this thing and takes three different aspects. First of all, the test and training data, the algorithms, and then it takes the hyperparameters to these algorithms and keeps changing values and playing with different combinations to give you the best outcome in terms of performance or measurements. So think of it this way. If I'm kind of like, I study something and I go give an exam, based on my grades, my parents are going to tell me whether I've done a good job or not. This is sort of what it is, except this AutoML model is perfectly capable of going through a whole bunch of stuff and telling me, is this good? Is this not good? Which one should I pick? And which is the best model among all the combinations of models that the system has gone through. So remember this term, AutoML. That's a way to do this, okay? We'll go through two quick examples, okay, of how we internally play with this. So first of all, how do we do workload detection? Workload detection is, if I have some users on a machine, how do I decide if there are any abnormal issues, or there are too many people on the machine, or somebody issues a big query that's running on the machine that's consuming more resources and starving all these other people? So the trick is, we basically take this model and we train it using three different methods: isolation forests, one-class SVMs, local outlier factors. Each model is evaluated using a certain set of test scores, and the confidence for this has to be greater than 92%. Usually more than 7 days of continuous rolling data helps the model become way more accurate. And if you maintain about 31 days of data, it becomes a lot more predictable. Now, what are these various algorithms? Isolation forests, they are used to identify anomalies rather than basically profiling just normal data points, right? So outliers are less frequent than just regular observations. So what we use is, we use something called randomly separated decision trees, because these outliers will be found at the root of the tree, which has the fewest number of splits, all right? So if something is deep, it's harder to isolate. If something is up, it's easier to isolate. So this is isolation forests. And how does this work? We randomly select a dimension that we are using for workload. You can see the dimensions on the left side. These are average active sessions per core, per CPU, response time. We feed this into isolation forests, and we apply this algorithm where hx is the path or length of the observation. And this is basically looking at the average path length in the unsuccessful search of a binary tree. And the algorithm is returning -1 in case it finds an anomaly, and 1 in case it finds something normal. Whenever something is detected as an anomaly, we automatically take an AWR, an ASH report of that particular session to flag it so that somebody can take a look at it and tell Is this good or bad? One class SVM is another method that's also used to identify and look at a training set. One thing I wanted to cover here is there's something called an RBF, or a radial basis function. This is something that is constantly used to find if your data is in a straight line, or what they call as a hyperplane, and if that can be used or not. A hyperplane is a common term in machine learning, and it's basically trying to identify which points are basically within the certain plane, and they are related in whatever ways. And then this can be used to classify this data. This is one class SVM. This is another algorithm. And again, we do the same thing. We take these things, we group them together, we find the outliers, and then we can track this across various performance dimensions. The last one is local outlier factor. This is another algorithm. So the reason I mentioned all these things is giving you as much information about what are the various algorithms we have, how do we use them to find. Of course, this is way more infinitely complex as compared to how I've made this in the slide, but it gives you an idea of how you can play this. So a summary of this whole thing is, once we process this data and use machine learning, we can predict when the workloads are basically anomalous. So the black lines are the actual lines, actual workloads, and the blue lines are the blue lines and the blue boundaries are basically showing us the forecasting ranges. What is the lower range and what is the upper range within this thing can be gone. One more way, we have a tool for database performance. It's called Cluster Health Advisor. DBAs can use this to basically detect performance issues. It directly reads a whole bunch of stuff from the OS and the DB, and it tries to give you root cause analysis of how this thing is going to cause a problem. It uses something called a Bayesian network system or engine, and that is what is the kind of the secret of how this internally works. And it detects things by applying these sequential probability tested filters, and it looks at statistic time to failures. Is this thing going to cause a problem or not? The estimation is called a non-parametric multivariate state estimation. I've tried to put some explanations in this, but think of it this way. Whatever you observe, if it's not normal, it'll calculate a residual value. And based on that, the fault detector will let you know if something is right or something is wrong. And then it classifies them saying, hey, these are way too high. And it says, oh, if these are the various things that are happening, then this is what can be causing a problem. But as DBAs, how do you use this machine learning thing, right? You just have to run charctl to monitor your databases, verify that the charctl commands are working, and then you can run charctl query diagnosis. And this basically runs on your system, uses this Bayesian machine learning model, and predicts and tells you when and what is going wrong in your system. Let's take a step away, go into dev zone, right? This is a topic that I wanted to actually go more into depth, but I knew I wouldn't have time. But here's a cool thing. There are many other people covering this session. So there's this thing called machine learning notebooks, which are Zeppelin notebooks within the autonomous database. And there's a lot of ways to create machine learning notebooks. How do you play with this and this? OML for SQL is what is actually there here. OML for Py is going to allow you to do Python-based workloads and also interact with scikit-learn and some of these other frameworks like Torch, PyTorch that are already there. Inside the autonomous data warehouse, there's this Zeppelin notebooks that are basically allowing you to run ML directly on top of the database. Here's a simple example of an attribute importance model. I'm not going into this in details because this will be covered in another presentation. The thing I mentioned about AutoML is this is going to be present in the next version of the autonomous database. Is we're going to basically have this where you can select something, and by default, we'll calculate auto attribute importance, as well as you'll be able to queue a bunch of stuff that runs against a different set of algorithms automatically. And you don't really have to care about what these are. And it will tell you which ones basically are good and which ones are not good. So it will automatically support this AutoML framework for you. These are two new algorithms that are present in database 20C, which are basically called gradient boosted trees. XGBoost is a very popular algorithm for classification, regression, and survival analysis, as well as anomaly detection. And MSET SPRT, which is basically stands for multivariate state estimation techniques and sequential probability ratio tests. And this is something that we have implemented it's used for mainly anomaly detection for monitoring critical processes. So these are available as part of the database from 20C and out onwards. Now, there's one last aspect before I close my presentation, and then we can go into questions. Oracle also has a cloud data science platform. This is a generic platform. This is not related to the DB per se, but can connect to the DB if you want to. It's a complete framework that gives you projects, notebooks, version control, whole bunch of users, use case templates, access control. You can do model, deployment, monitoring, everything. And all these features are present as part of this platform. The only difference is that this is a generic platform. So you can run scikit-learn, TensorFlow, any of these other algorithms on it and connect it to OML if you want to. OML only runs on autonomous and is usually tied very close to the database features that you have. So if you're a DBA, most of your data sits in Oracle, you can use OML without kind of spending too much time trying to play with this stuff. If you're a generic data science guy, and you can play with anything and everything, you play with pandas data sets, you use NumPy, SciPy, and all of these things. You can use this Oracle Cloud Data Science platform, which does feature selection, model evaluation, and all of these other features that I mentioned, including visualization tools. So this is basically, imagine all the open source stuff that's available in the Oracle OCI Cloud. It's called the Oracle Cloud Data Science platform. Now, 45 minutes is a very, very short period of time to cover so much things. But the good thing is, and thanks to Francisco, who's basically doing this along with a whole bunch of volunteers who are doing this excellent conference, there are a bunch of sessions. Now, I'm biased, and I think some of these guys are going to cover this. And Charlie's going to talk about this whole thing of how do you actually start writing code and implementing things. Heli expands way more into machine learning details. There's a lab, and Francisco talks about stuff with OAC, and Kai will talk a little bit more about ADW. And if you want to learn about analytical server, Edelweiss covers this. So these 6 topics branch off my topic, my session that I have done today, and kind of takes you to the next level. And I hope this was useful. All right, so I think I'm just on 45 minutes. I'll take a couple of questions if you guys have any.
Well, thank you, Sandesh. That was very enlightening. I haven't seen any questions in the Q&A yet, but I'll give people a moment to see if they've got anything. I had one kind of question myself. You said you were talking earlier about the model builders versus model consumers, and that's something I've really noticed in the last year or so, maybe, is that are you seeing sort of the availability of these sort of pre-trained models is starting to really ramp up now?
Oh yeah, absolutely. Yeah. So the thing is, I'll tell you this, the whole machine learning space has quite dramatically transformed, okay? In order for you to get started with some of this stuff, you probably need a week. Most of the stuff is stuff you already know. Like for DBAs, there's a package called DBMS data mining. If you actually start exploring the procedures of that, you can write a ton of code in PL SQL that basically does machine learning based optimization on top of data that's already sitting inside an Oracle database. That's actually pretty cool. If you're a guy that is used to working on scikit-learn and you want to intersect with some of your data that's actually there, you can use OML for Pi that allows you to basically create these proxy data frames that operate on top of data that's actually sitting behind the Oracle database without actually learning a single line of SQL. So in other words, I'm a Python guy, I hate SQL. Can I work with the data on the Oracle database using machine learning algorithms? Yes. AutoML, basically it doesn't require you to know any algorithms, nothing. It just takes, so think of it this way, right? Imagine I have a query and I have some data and I just run it and I run an advisor and the advisor tells me, create this index, run this query, this is the best plan. That's basically what AutoML is. I give it the data, I say, you go figure out which algorithms and which hyperparameters to specify. It will do a Cartesian product or something less than a Cartesian product of all these things, play around with different combinations and say, hey, look, I did about 500 runs and this turns out to be the best combination that you need for your use case. You look at the output of the model and say, does this make sense? If the output looks like garbage, that means you probably gave it garbage in the input or some attribute was not right. And all you have to do is just go and say, hey, you know what, just try these combinations and let it rip again. You can do this today, right? Like about 5 years ago, most of this stuff was not even there. So the platforms that are around this are starting to develop. More and more of these algorithms are basically available as reusable libraries. So it's becoming extremely easy to basically enter this field, even though you have no ideas of maths or stats or any ways these algorithms actually function. What you need to know is how do you apply these algorithms to your business use cases? You need to be smart about that.
So we're almost getting to the level of with machine learning now that we got with stats some years back with the
Pretty
likes of
much.
stats.
Pretty much. As a matter of fact, I've seen developments that are designed to write code, designed to review code. It's if you see the developments that are happening, they're so mind-boggling. It's just like, it's like, for example, the things that are happening in the machine learning space for cameras will basically make DSLRs obsolete. The things that are happening in the developer space could basically not require to write any code. I mean, imagine not writing any code. That doesn't make any sense to me. But if AI gets to a point where it can write some good code, all I have to do is say, hey, this is what I want you to do. Go ahead and do it. And it writes all the code for me. And I'm not talking about a 4GL, right? Which kind of just pulls out something from a bunch of reusable stuff. And this thing actually looks at my code and says, hey, this is probably a better way to write it. And it's not just a syntax checker, right? So there's a lot of interesting things happening in this space. AI is potentially going to be one of the biggest job disruptors for us of our times. But I'm saying that in a very positive way, because it's basically going to crack open problems, and it's going to make us way more efficient in terms of data analytics as compared to how we have ever been for the last 50 years. And this can be done by somebody sitting in a laptop, accessing the cloud for $200. It's so damn incredible.
There's no other questions in the Q&A. So the other thing
I think I've stumped everybody. That's what I've done. Either everyone is asleep or I've stumped everybody.
Yeah. One other thing I was just looking at was, Zeppelin is something I've been meaning to look at myself. It's sort of been in the queue for about the last 6 months, but with all the lockdowns and what have you that's been going on everywhere, it's sort of other things.
Have you used Jupyter before?
I've used Jupyter quite a bit, yes.
It's the same thing. It is just the same.
That's what I was wondering is what's the...
As a matter of fact, Jupyter is way better. Jupyter is way better. But the difference is that Jupyter has a different kind of open source licensing, which kind of like makes it harder to embed in environments. Like when we started working on it, Zeppelin is straight up Apache.
Yeah.
So it becomes extremely easy to embed it into any system, right? Whereas if you're looking at licensing considerations, it might have changed. This was something that was like 2 years ago. I don't know what the present state of this thing is. So please don't quote me on this one. But the way I look at it is they're functionally identical, but Jupyter Labs has a much larger community behind it. If you look at in terms of the number of check-ins versus if you look at scikit-learn, Anaconda, TensorFlow, TensorBoard, PyTorch, if you look at any of these frameworks, they're all in Jupyter. So Jupyter Labs is definitely way more popular as compared to Zeppelin. Zeppelin just looks like a more older version of Jupyter Labs, but functionally they're absolutely identical. So if you already know how to use Jupyter, there's no need to learn Zeppelin per se. You just be at home.
Oh, that's easy. Oh, we've got an actual question. So someone's asked, how does it differ from the machine learning functionality in OAC?
Machine learning functionality in the OAC is slightly different. So the other one, so there's some basic analytics in the DB, which is what is exposed as part of OML. OAC basically adds another layer of analytics. So a whole bunch of these tasks, they're like a bunch of automatable flows in OAC. That's why I mentioned you should actually attend Edelweiss's session. She covered a lot of examples. Edelweiss and wait a second, I think I always get mixed up between who's covering this. Francisco is basically covering most of these things as to what are the various kinds of scenarios in this. So what OAC uses internally is most of the functionality that's actually coming from OML. So think of it this way: database, core packages that implement algorithms, PL SQL interfaces that expose these algorithms, further packages and interfaces on top of them that build macro functionality on top of this thing. So if I already know like attribute importance is an example, right? So I can just pass some inputs and say, you go figure out what's important and how do you go about doing it. If I use just OML, I may have to write a little more code. Of course, not with the new version, but with the older versions, versus OSC has this as part of the package. So one of them is a analytic suite of functions OML is just basic functionality of implementing machine learning, which is what OSC uses internally to provide all these additional value adds.
Excellent. Oh, thank you. So that's no other questions have turned up. Oh, I see.
Oh,
sorry,
see
things are changing in the panel. So yeah, no, that's it. Okay,
I'm telling you, either I have stumped people or everybody's there. But I can tell you this. This is just a good introductory session, right? See, I went through so many terms, but I mean, it's taken me 2-3 years to learn this stuff. So if you kind of like, you're completely bamboozled by the stuff, don't be intimidated. First thing. Second thing, this stuff ain't as hard as what you think it is. It's just syntax. It's just a new feature. Think of it as, hey, you know, this is like Exadata, or this is just like, you know, a new version of Exadata that came out. I just have to learn something, or a new database feature just came out and I have to learn something. And that's kind of what it is. As long as you treat it that way, it's actually pretty simple to learn. Once you start writing some of this code on it, especially I've seen this, there's a complete set of examples for DBMS data binding. And I think Charlie Berger, who's the PM for OML, will basically go through a lot of examples on this. So my session provides a base to all these other sessions. And that's why I've not covered too much of the OML functionality, how it works, how do you write code, syntax, screens. I didn't go into that. I actually spent more time covering the basics as to what are the various kinds of algorithms, whether it's classification, regression, clustering. You should know these things by heart now after my session. So when someone repeats these terms to you, you know exactly what this means and what kind of use cases these terms map to. So that's very, very important. Get your conceptual part right. And then it's just copy pasting code. You know, everything is Stack Overflow, right? It's just you copy paste code and you just kind of build stuff.
Okay, well, I think we can probably call it quits at that point. So thank you very much, Sandesh. It was excellent talk. And thank you everyone else for taking part. Don't forget to register for other sessions in the conferences. I mean, Sandesh has already mentioned half a dozen other ones, which should be really interesting to follow up on. And a reminder again that you can interact on the Hey Summit page, on the page where the session is advertised. There will be a comment section there for the next couple of weeks as well. And you can also look at the recording of the session. And so thank you very much, and please enjoy the rest of the conference.
Thank you. Thank you, and enjoy the rest of the conference as well, guys. This is really cool. Okay. See ya.
Well done. Excellent. Thank you.